people which are organizing this semester here, for giving the opportunity, first of all, to stay here and do research on this great institute, and also to give this talk. This talk is about a progress report based on the 3 papers, 2 are already written, and a third is just about to be written. So I should say it's going to be a. So this is not working well. Okay. This is a joint work with Kostatiros, which was a former postdoc in Toronto, now at University of Warwick. So as I said, this is a work in progress. The theorems not attributed are from these papers. The conjectures are also from these papers. Okay, so the outline. So I'm going to, so the thing here to notice is this dual Ramsey theorem. And what to explain this, why we call it a dual. So I basically started introducing the dual Ramsey theorem, and then go to a context, a structure or trees, and then try to dualize the part 1 on that context. So, okay, so what is the project? How do you explain this? So there is that the dualization concerned here inversing the mapping rather than coloring the injections. We are coloring the surjections. For example, in the Ramsey theorem, it typically is written in terms of partitions of the set rather than injections. Say K partitions rather than K element subsets. You're covering the K partition rather than K element subsets. You can also formalize this in a very precise way. I'm not concerned with this. The reason is because we are still quite far away to properly understand this dual Ramsey theory, especially dual structural Ramsey theory. See, this is attempt to understand the dual Ramsey theorem for trees, the simple structures, trees, rather than linear ordered sets. Linear ordered sets is basically the classical dual Ramsey theorem. So you want to add some structures. So the first thing to add is to understand the trees. So here the part 2 is to I'm recalling you a rather deep injective Ramsey theoretic results of hyperlikely, and this is what we have, the results, the new result that we have. Okay, so let's go. So finite union theorem, it's a rather simple looking result, typically credited to Folkman, but it's due to independently to Rado and Sanders. It says the following: you have a number for a given K and a number of colors, you have a number F, so that for every power set on a set X of canonicity bigger or equal than that, there is a family of, so when you color the power set, meaning all subsets of that are actually non-empty, really. Then you will find a family of disjoint sets, in other words, some sort of a copy, dual copy of K, so that all unions that you can form, non-empty union, are monochromatic. It's a one-dimensional dual Ramsey, so one-dimensional pigeonhole. So that's the finite union theorem. So it was discovered quite old. It took quite a long time to actually go to infinite versions. And also, you'll see later on that the infinite theorems tend to be considerably deeper and harder in this domain. I guess so. That's the prototype result, and it's in the simplest possible form. And now, if you are infinite, how infinite would look like? So it took quite a long time to actually get this way. So this was, by the way, the major progress in Ramsey theory. Carlson-Simpson paper was basically it's basically some sort of a revolution in that area. So what they have done is basically they lifted that theorem to infinity. So you're now now you're coloring the subsets of the power set. Of course, for this coloring, you have to make it Borel or something reasonable, meaning that you have Borel or something, measurable colorings. Then you have an infinite sequence of disjoints, and all possible unions that you can think of are monochromatic. They can form are monochromatic. So this is the infinite. This is again the one-dimensional. In some sense, it's a two-dimensional. This is this is a result. How would you, if you think about it in terms of partitions, that will be two partitions, because you know the other partition contains the zero. So I think this way is a better statement for what I want to say, and also to see this. And do a Ramsey theorem for the infinite. You will simply go to you're coloring the infinite families of pairwise disjoint non-empty sets. In other words, you are coloring all partitions in infinite of omega into many pieces. And if you want to find one partition, so all whose coarser partitions are more homotic. That's usually how this result is stated. But if you see, this result is non-trivial even if you didn't go to infinite, say, but say 3-element families of pairwise disjoint set. It's already a challenge, or even but I mean, this is the infinite one from which the finite follows. The finite, if I just to recall you, the finite one is a well-known result, which is really called the Graham-Rothschild theorems. They're rather well-known. So that's how this is done. So you have this finite physical principle. You have a natural question about getting to infinity, and you suddenly enter into domain of nice coloring, Suslin measurable necessarily, and then you have these sort of results. I'll later on point out about the proofs, how these results were proved, because they're going to be interesting for us.
What is this U of D?
U of?
The last thing, the U of D.
Yeah, so this means that, well, it's U of omega really should be, but okay, the U of D is so the set for, so U of D, so maybe this is typo, let me just see. I guess this is U omega, I guess. So all infinite, yeah, okay, so form a U of D is the all subsets that you can form by taking the unions of elements from D. So U of D somehow if you think of omega as a singletons, if you think of omega as a singletons, then that would be a corresponding notation, right? This is all possible. Yeah. I should have a little definition here about that, okay. Okay, so now we will come back again to this. Now I want to expose you some important injective, not dual, about the trees. Actually, perhaps the most important, such both in the finite and infinite case. Okay, so I need some notation to express this because again, so you have a tree which is a rooted, finitely branching with no maximal nodes. These results are going to be all interesting even if you take a binary tree, some fixed degree, or even a homogeneous trees, etc. But it's very important for a general, if all finitely branching tree with no terminal nodes. So this is the object that we considered. We have this notation, and there's this notation I needed to tell the nth level. So the nth, so distance from the root n. Okay, so these are these nth levels. And for a subset of the tree, I look at the level it hits. So the level set of D. I need that notation, so there's typically you skip some level. Same thing is for the subtrees. I mean, you have you can think about D as a subtree. Its levels may be quite different than the levels may have nothing to do with the levels of T. But here I record how the D acts on the levels of T rather than D itself. Okay, now we go. What is more interesting? Go to higher dimension. So I take a D vector of such a trees. Or again, the same sort of a trees. And now rather than okay, so it's just trees. So rather than so now I would like to go to talk about the subsets of or some sort of a tree associated to it. There's a natural tree associated to a sequence of trees. This is this tree product, union of products of levels. This is a tree under Cartesian ordering. So and each level is exactly the product of nth levels, so there's no surprises here. Otherwise, if you take, for a static result, actually you don't need that, but the point of the complementarity theorem is not really in this, but in the notion of a largeness. This is this domination. Okay, ordering is the coordinate-wise. Successors are these, as you could imagine. And now a sequence is called vector subset. And now we see vector subset being a subset of, for each di is a subset of ti, but important thing is that they have to have the same levels. They have to hit the same levels. So I don't consider oscillation. Or there is a corresponding. So in some sense, think about the d as kind of di's as a subsets of di which hit the same levels. And now there's the key notion of a density. But maybe here we have to pose a little bit. So this is kind of it is a metric notion. The T itself is a kind of a metric structure. And these epsilon densities correspond to what people call epsilon net. So what it says, for every n, there is an m. So large enough so that everything on the nth level and above T, by the way, think about the T root. So there's actually no successor. Everything is there. So everything is dominated by something. So D dominates. In other words, if a D hits levels L1, L2, etc., then say typically you would say LK level dominates, LK level of D dominates the K level of T, point-wise, you see, on every point, for every. So there's that notion of a largeness. So you see, this is, maybe a better name would be a T, it would be a large, T comma little t large, or a T large. So that's a notion of a largeness. So again, is Ramsey theory, usually you count the large structure by numbers or being isomorphic to some structure, having us. Here is the tree itself gives you notion of largeness. Notice that this notion of largeness changes as you change the levels. From the canality point of view, the tree can be profusely branching, so higher the level is, the more things to dominate. So there's actually no, so typically the usual inductive proofs here will not work. Usual inductive proofs for these sort of results. Because typically you don't know how big homogeneous sets or monochromatic sets you need to construct, because it depends where you believed you will be able to build your large. And this could, okay, the dense means dense everywhere about the root. So actually, this is that example for D, which is the first level of D dominates the T, the second dominates immediate successors, etc. That's the picture. So it could be and that's the result of Apolloically, 1966. Was motivated by a problem, by a consistency result in set theory. It was a crucial lemma for producing a model of a ZF with no choice but with the Bruin prime ideal theorem being true in the model. Okay, so you have vector tree, you have a vector subset which is dense, arbitrary. Then for every coloring into two pieces, P and its complement, you see, this is an asymmetric version of this. The only two color P and its complement, there exists a subset dense, which is either, there is a vector subset which is either dense everywhere and is a subset of D. I mean, either the first color is very large or the other color is somewhere large. The P complement is somewhere large, but in the same sense. So this largeness is controlled by T, by the trees, and that's that. This maybe is difficult to adjust why such a theorem would be rather important, but I guess maybe you could try to reformulate it in the metric terms, and you'll see it's actually a very natural mathematical statement about the epsilon nets in the product of space. The product of metric spaces become a rather natural statement. But for the trees, maybe not clear why this is a Ramsey theoretic statement at all. I mean, typical. And that's, you see it by going to a different notion, a strong subtree, which looks like a weaker result, but actually is equivalent to it. and it's more in the spirit of the classical Ramsey theorem, or the Ramsey theorem itself. You know, because you're typically you're carrying the copies of a structure, the morphic copy of some fixed structure. That's in Ramsey theory. That's what you usually do. And there you are carrying something. You have asymmetry, and so this is how you get asymmetry. You have the notion of strong subtree. So height is a subset which has a root. Every level of S preserves the levels, although different. You know, it might skip some level, but every level of S is a subset of some level. And that key, number 3 is key thing here. If you split, if you decide to choose S, little s, in S, then you must extend inside S all immediate successor of S in T. So this was this big tree T gives you a notion of a largeness which you must respect. So that's the point of this.
Go back.
So yes. So it's some sort of a copy of the tree. It's still a very nice copy, in a sense, the most natural thing. What is unusual here is that you must preserve splittings, but in this sense, sorry. You must preserve branching. Yes.
Over there, by the level of S, you mean count?
Level in its own order. Its own level is a subset of the level of T. In general subsets, this may not be true, may have nothing to do with each other, but here you want them to do. In some sense, if you think about the T to be a binary tree, complete binary tree, then S is literally its own copy, very natural copy, literally isomorphic copy. But if T is profusely branching, this is something else. And in some sense, the power of the theorem becomes exactly if you use the profusely branching trees. This is a possible way to think about that. Okay, you choose the root, and then you must extend all immediate successor, etc. On some level up, there are lots of things to skip. I guess if you think about the inductive, if you think about you want to prove this Ramsey, try to prove, this is, by the way, good exercise. If you've never seen this, try to prove this result in one dimension is not quite trivial, although you would expect to be rather simple in dimension 1. Not quite trivial because you have to respect the levels. In other words, you cannot use the obvious fact that if you have a subset of the tree, then its complement must be somewhere dense. It's not as obvious as that. Slightly more complex, but not very much. And now we have to go to a dimension T. So you have to, again, vector strong subtree, meaning the strong subtrees, the level sets are the same. And this is the strong T version of here pointed by Lever. This notion of strong subtrees was a great invention, because first of all, you don't lose the power of the theorem. You don't lose the power of the theorem. Very easy to deduce one from the other, vice versa. But what is interesting here that you can build Ramsey theory on it. You take this as a one-dimensional physical principle. You can go to high dimension, even the dimension infinity. For example, you can have a theorem which says that if you have any finitely branching tree, then if you fix a k and you color all strong subtree of height k, then there is a strong subtree of height omega, so all whose strong subtree of height k are monochromatic. And if I notice if the tree is profusely branching, strong subtree of height k are not necessarily isomorphic to each other. So you are really coloring non-isomorphic structures. So you would say, why I could not find a bad coloring? What's the reason? In the usual Ramsey theorem, all k element sets are identical, I mean isomorphic. So you know here they may not be, and still you have the exact analog of the Ramsey theorem. But I will not go to that direction. I try to dualize this theorem. In other words, the attempt is to say, okay, I have this deep theorem about injective theorem about trees, haploid theorem. I want to find its dual form. First of all, I would like to do it in dimension 1 first, and then climb up dimensions. So dimension 1. So again, what is analogy? Analogy is very simple. I mean, omega is a tree, right? It's a branch. And now so I look at this Carlson-Simpson on omega. I try to put it on the tree. So very simple as idea, right? Unfortunately, it turned out to be a rather difficult task, more difficult than we thought. Okay, so we have this stuff. So we try to color the subsets. We now we write to again think about T as if single trees. You want to color the subsets of a tree, and you have a Ramsey theorem there. And obviously, the opponent can look at what are the minimal elements of this subset. If there are more of them, then can color the mod something, the cardinality mod something. So there is no Ramsey theorem there, right? Because if you want to have a large, so typically you want to avoid this. So therefore, you add this condition of a minimum, that every set has a minimum. Otherwise, you want to avoid this bad coloring. Again, if you allow sets of arbitrary beginning minimums, then you don't have a theorem, don't even have a Ramsey degree. I mean, you can't even have a bounded number of colors. So this is a natural thing. That's what you want to color.
What do you mean by minimum? Is
the minimal element. The minimal. I mean,
just a minimum.
Yeah, one element. It's a root. Although they may not be trees, so they may not be subtrees. But anyway, subset which have a minimum.
So it has no predecessor.
Yeah.
Everything is
Use a subset. This cross. Look, cross T is a tree. Cross T is a tree. Yes. The minimum. So it has a minimum.
minimum, not minimum.
That was my question.
Yeah. Okay. I'm not sure my English is so good to put where I should put. Yeah. Okay. I see the difference. What should I say so this is clear? I want the set has a minimum. Least element. You see, on omega, every subset has a minimum, right? So we don't, in the Carlson-Simpson, you don't say this, right? But that was important thing, as a matter of fact. So there's a minimum. And there's, of course, there's counter topology from there, simple metric, compact. Okay, so D subspace. What is a D subspace? Well, now we like to say this subspace is something large, something that you like to, which means some sort of a dual copy of T itself. Because remember, you want to color the surjections. So you want to get the monochromatic thing should be some sort of a dual copy of itself. So this bold-face D is that notion of largeness has to be a. Okay, so it's the family which is indexed by some vector subset. D, product of this, yeah. They are disjoint, as we had before, and the minimum is itself. Minimum of UT is T. We are coloring. So this is the large subspaces. These are the objects that we like, if D is large. And of course, large D, you can even guess which condition on D I want. It has to be dense. Because that was the part of the Halpern-Loihy theorem. That was the condition of Halpern-Loihy theorem. That's what we wanted there. We wanted to have a monochromatic dense set or a somber dense. So that's how this is this chaotic thing that it looks like, which means that you have to produce something like that. In your monochromatic thing has to look something like that. Should start somewhere, and then whatever D tells you, you have to have there, and the sets are disjoint. And I put this picture. Is there? This picture is not troublesome if you think that you are coloring just a single element, just one such a blob. But if you color two such a blob, this is the nightmare. This is a mess, because if you see two such a blob, you see the way how they oscillate. So the opponent can give you a very bad coloring, meaning that you can't stabilize the color. So, but anyway, at the moment it's okay like that. Okay, it's the span of these all unions that you can form, provided they have a minimum. The span of such as all the unions that even infinite union, provided they have a minimum. It's rather natural. And one is subset of the other if all elements, if this collection is a subset of the other collection. The elements of one is obtained by taking the union of the other. And notice that if I know that the subset, then I know that the index set is also a vector subset of. It's not difficult because minimums set knows this minimum. So. And this is the theorem. It's exactly what was in the Halpern-Loihy, only the dual form. So again, we have vector tree, and the coloring of all subsets of T that have minimum, that with a minimum. And take arbitrary dense vector subset and possible choice of the blobs with this index set in this subspace. Take your favor this subspace, indexed by that. Then there is a further subspace which is inside the blue, or it is, and it's moreover its index set is dense, everywhere dense, or there's a subset which is red and its index set is somewhere dense. So it's like Halpern-Lökli, but only the dual form. This is, you can also think about this as a surjective map. This is exactly the dual form of the Halpern-Lökli. So that's the theorem that you like to prove to give you some sense of what it involves. So this is the one-dimensional result, one-dimensional result. Coloring is just a subset, rather than pairs of sets, triples of sets, etc. We'll think about this later. We'll come to that later. Okay, let us see how. First of all, consequences. Consequences maybe are easier to think about in the terms of the strong subtrees, because remember, in the strong subtrees, you are having a copy of itself. So you have vector tree, strong vector subtree, and you have a family of these blobs indexed by it. Then you can refine it to be monochromatic. So now it's a symmetric result. It's a very finite coloring. There's a family of these blobs indexed by a strong subtree, which is monochromatic. So this is the one-dimensional. This is a dual version of the Levers result. And the Carlson-Simpson gets because the omega is a tree, right? So there's always a minimum. Okay, so that's the one-dimensional case. And how do you prove? Now it comes to the question: how do you prove this result? And maybe part of the reason why I wanted to expose this, because if I think currently there is quite a strong push towards developing the dual Ramsey theory. And I noticed many of the dual structure around the theorem. If you know a little bit of structure around the theorem, you will see that the Hell-Dewey theorem is rather important there. The classic, I'll state it in a moment, and here it is the result. Actually, very well-known fact, one of the cornerstone of the field. So you are coloring what? So you have a number of colors and a number of letters, finite alphabet. You look at the L words, C coloring of L words, and there's a variable word, meaning there's a variable shows up, and all substitutions are monochromatic. Computational line, typically people call it computational line, which is monochromatic. So the structural Ramsey theory uses this principle as one of the crucial. Now you will see in the way that we are proving this result that we actually have to modify this considerably, which means that if you want to dualize some particular Ramsey theoretic result, you have to develop the corresponding Hell-Dewey theorem. They tend to be very, very different, not obviously related to the original one, although the language is useful, meaning that this idea is useful. Okay, so that's the classical. And you see, a part of the progress, why the Carlson-Simpson had the progress on the result, is exactly because they were able to prove this analog of the infinitary Hell-Dewey theorem. Because if you call it a semigroup of words, there's an infinite sequence of variable words, and all of the concatenation. Very interesting here very important here to see which concatenations they decided to do. They decided to start from 0 and run all integers all up to n and stop. So you can imagine a little bit more challenging thing, actually considerably more challenging to try to skip some of the indexes. And still, this is also possible, but not by the methods that they had. This was deeper fact. This one has a considerable story around it. There's even a density version of this result recently proved. Well, there is no density version of the other one. We call it a conditional. This is the conditional span of this conditional, meaning that you rather unconditional, that you say xn0, lambda 0, concatenated with xn1, etc. Okay, so that's the key for the Carlson-Simpson. I guess it makes sense because if you think about what these blobs are. These are really you can think about as a variable words. So yeah, with the one actually the alphabet 0 and the one variable. Because somehow it's not it's not so unnatural to actually try to that. Actually, that's what the calculations have. Now we have to adjust this for trees, and let us see what that is. And okay, so again we have a vector tree or a single tree. I guess maybe I should have said it just for one tree, and this is interesting, one single tree rather than a vector tree. Okay, so what are now words? Now words are located. They're quite conditional. They have to live on a stripe. They are plugging the digits there, or from the alphabet, the letters. So that's what. So these are what the words are. And this is what, unfortunately, this is highly conditional because you have to respect the structure of the tree. You can't skip or can't put them independently. These are the words that are defined or on the stripe in the tree, level, for example. So this is how they look. So if you have digits, you're adding there, you're labeling them. You're labeling on a particular stripe. And then of course you are concatenating in an obvious way. I mean, you can concatenate in an obvious way. If a top of one is the bottom of the other, you can concatenate, take the union of the function. This is a function, right? So, okay. And the variable words, that's more challenging. What's relevant here? Because there's some time to figure out what is relevant here. So variable words must be indexed by a level. You see, there's on the boldface level, vector level subset. So this is the sequence of subset. Each subset is a subset of a single level. So there's a single level, so the di is a subset of the T1. D1 is a subset, T1 and K, I guess, K in between. And D2 is a subset of T1K, etc. So a level subset. I'll give you a picture. So, and natural thing. And now what is a natural thing? You're allowed to use variable. One for each different variable for different S. And okay, so what it is? So again, you have a minimum. S is a minimum, or the places where you put a variable. And now there's that interesting thing that you don't want the opponent to have option to color, to give a bad coloring. So so there's no oscillation between two different variables. The level sets are the same. The levels that are hit are the same.
U sub S and V sub S the same? Or?
This is typo. This should be V. This is typo. This comes from copying and pasting somewhere. Yeah. Sorry about this. Yeah. Okay, so that's how they look. So if you take a 1, VS0, it acts here, VS1 acts somewhere, etc. They must intersect the same levels. If you pick in a 1 or in some level, the other one must have something there, although not copying or something. That's more or less how the variable words look like. So there is the variable span is D. That's a notation. Just bottom is M, top is N, etc. And then you are doing the usual. So you are taking M less than M, or possible M less than N, and the all possible vector level subsets. You see, only one for a fixed 2M, and then only one set there. Okay, so this is the collection of variable words. And now you can do obvious substitutions. There's nothing surprising here. You substitute VS by AS, so there's no substitute. So all possible substitutions is this notation, all possible. This corresponds to a commutative line in the classical context, the constant span of S, so commutative line generated by F. And now subspace. Subspace is given, you see, a subspace now is given by a sequence of variable words, infinite. Somehow it corresponds to the subspace that we wanted to have in that theorem that we are trying to prove. So the bottom of the first is 0, and then they climb up one after the other. The index, the variables, the index at the i's must be they are vector subset, meaning that they are going to hit the same level, and one for each index n, and they have to be dense, meaning we are not interested in the subspaces where the indexes are not large in the sense of original tree. So we are just interested in that. And then you look at the corresponding constant span. So this is a large subset of the set of all words that you can obtain. All this is rather natural. And you have for two subspace, write x less than y if the corresponding constant span is a subset. That would also imply, as before, that the index sets di's have to be subsets of the corresponding for y. And this is the infinite algebra for trees. This is the heart of the matter of that other result. It's actually Pigeonhole principle for some other results. It's interesting, which is a divergence from the Carlson-Simpson methodology. They could deduce the theorem from the corresponding version of that, but we could not. And the reason is a compactness of that space. Here we cannot. We have to actually build another infinite dimensional version of this. But anyway, let's finite dimensional says what rather similarly what was saying in the Carlson-Simpson case. So we have a vector tree, finite alphabet, finite coloring of the constant words, meaning no variables. Then every subspace has a further subspace whose constant span is monochromatic. So notice that's interesting here is that these the lengths of these stripes, as you define, they get bigger and bigger. So it's interesting. Suddenly, you for a finite coloring, you have for a complicated coloring, you will probably perhaps need to take a faster sequence. But what is interesting that this, even though you are taking the faster sequence, what's important, and actually that's the whole difficulty in this result, is there is that index set of variables, is di, d, and these sets, as you go up, they have to dominate more and more levels. They have to be large. They cannot be. You cannot shrink them too much. They have to dominate corresponding levels. For example, this has to dominate some level. If this was increasing enumeration, then this has to dominate some level. This other one's a little bit bigger level. This other one bigger, etc. So they dominate eventually all levels. So what I'm saying, inside this result is also a hyperlogically result there inside. It must be, right? Hyperlogical theorem must be inside the proof of it. So it's not. Okay, so now to actually prove the result that we wanted to prove, we have to, we have to go to infinite dimension. So you have to infinite sequence of words. You have to have a result for the coloring infinite sequence of words. Remember, because we are interested in coloring the infinite sets. But if you kind of imagine that these blobs there are finite, then in some sense that would follow from this Hell-Dewey theorem for finite. But we intend to color infinite ones, so therefore you have to have a coloring result for infinite sequences. And so we have a natural thing there. So there's a sequence of the words with no variables, so that they match each other in the bottom of the next is the top of the previous. And for a given subspace, they cross all these words that you can find inside the span. Or like in the Carlson-Simpson, you take from 0 to n. The span up to 0n should be inside. So that's the infinite sequences inside the subspaces. So this is a relativized version of the infinite sequence inside the space. And that's the infinite one which we needed for the. So we have a finite hover, then every nice coloring of the set of words, and every subspace is a further subspace of all whose sequences that you can find there, infinite sequence that you can find there are monochromatic. That's the final. From this is rather simple to prove the other result. High dimensions. And now that's now a very interesting situation. First, so what's the problem? High dimension. So now we want to color the two globes. And suppose we want to do something so that the minimums are related in the tree ordering. And here's the bad coloring. You look at this level and look at the parity of this, or modulo k, something, parity of this intersection. So there is no even finite degree, so there's a problem. So if you want to color the pairs, you have this bad coloring. You have two blobs. One, suppose that you have to decide which two blobs, they're always related or never related, whatever. Let us look at the related. Then you can do this. So there's no even finite degree. Okay. So that's what do we do? Well, I guess in Ramsey theorem you don't prove what you like. You prove what you can, what must, meaning that you are computing Ramsey degree in some sense. You don't have option. This is the bad coloring. You say, well, I found one. Maybe tomorrow somebody is going to find me another one, etc. This process never stops. And it turns out that actually that's the only one. There's no other. That's the. But before I motivate this, I want to recall you rather deep result. Do a Ramsey theorem of Graham-Rothschild in this particular form that I call. In other words, I'm not saying k partitions, ignoring the one cell of the partition, the one which contains 0, if x is a set of integers, or initial segment of integers. So again, so what it says, there is a for every k and L, so this is the k-dimensional version of the result. C, number of color, the L is the space that you like to have. C is the number of color. There is an integer, rather large, but not particularly, not very. Today we actually have a good bound on that. Okay, so that if you color all k families of pairwise disjoint subsets of X. So remember there we just look at the k equal 1. So just one subset. There is a family which has a L many sets disjoint. So all further k element subsets you can form inside this Markov matrix. That's the dual Ramsey theorem. There's literally a finite dual Ramsey theorem where injections, rejections are intertwined. Graham-Rothschild result is very useful, very easy to use also. So good to know. It's a result, one result which is in the dual theory. If you don't know any result, this is the one you should try to remember, because it's easy to remember. It's simply okay. For example, try to use this to show that in the, say, the class of finite graphs, complete graphs have a degree 1. Coloring the, say, k clicks. And the reason is why? Because every graph is a disjointness graph of family of sets. So this result gives you that. What I'm saying is very easy to use result. And also gives you rather, it shows you how much more powerful is than the injective. Okay. So this is the compromise. First compromise. We bound the degree. Degree is now fixed bounded. So it's binary, ternary, etc. trees. And now, so that you avoid this coloring, so you don't allow the other node on the same level. So you, in other words, you want to have a copy of the tree, but a little bit skewed, so that the opponent cannot use this coloring. So this is, we call it a skew subtree. It's a rather natural, okay? T has a minimum, every maximal J has, it's a very nice tree of, in other words, the copy of a B to the less than K. Literally is a morphic copy, but in some particular way. Immediate successor have to extend immediate successor, the same as in the notion of a strong subtree. So the notion of a largeness which T imposes is respected. And now the new thing is that every level of T, every level, Tm and every must have a different heights. They are on a different heights. They're never, and moreover, on the same level, they are different heights. Respecting less Hach ordering. Of course, the reason is because if you don't reflect, the opponent can give you coloring how these oscillate with that. So let us say there's no oscillation, they respect each other. So this Q subtree, I guess there's a picture, you can imagine it, I guess you simply go sidewise respecting the tree. A subspace, again, subspace would be a subspace. So what is that you are looking at all sets that have a minimum as before, but except now you go to dimension k rather than dimension 1. So a k-dimensional subspace is the one indexed by Q subtree. Usual as you would expect, indexed by Q subtree. A k-dimensional subspace, as in the case of the Graham-Rothschild, is a collection of k pairwise disjoint sets. There, because the tree is omega, everything is nice, everything has a minimum, and everything is a skew subtree, and everything, there's no, anything you want is there preserved. And now further subspace, you would imagine that the elements of this further subspace is obtained by taking the union of the previous subspace. So it's another natural notion of being a subspace, further subspace. And this is how they again look, except that now, as I see it now, that think about now that you are coloring now more than one blob. So now they can, for example, the relationship of these two blobs there is quite different than some other two in the same sort of position. So this will not be monochromatic. So that's basically sort of a thing that we have to solve. Okay, so this dimension k and this theorem is true. There is a number. So there is a number, so that for every integer bigger than that number, let's look, yes, there is a typo here, this R is C. This R is C. The number of color is C usually, okay. So your coloring, C coloring of the k-dimensional subspace. There is an L-dimensional subspace, or all further k-dimensional subspace is monochromatic. So it's exactly the dual Ramsey's for trees. In the category of trees, where the strong subtree is replaced by skew subtree. So you are losing the strongness, but which means that the only thing that you're not respecting are the levels. Everything else you're respecting, and you have a dual form of the result. And this result is several degrees, about, say, 5 degrees more complex to prove than the one-dimensional. So basically one paper for that. Okay, so this is that, as you would expect. And the further work, which is now in progress, which you basically go to dimension, infinite dimension. So you want to have an infinite, you're now coloring the infinite subspaces. So as in the case of the Carlson-Simpson, you're coloring the infinite sequences of pairwise disjoint sets in the Borel way or Suslin way. Here you are coloring the infinite collections. You are coloring the collection of blobs indexed by infinite skew subtrees of infinite height. In a Borel way or a Suslin way. And at the moment is a conjecture which we are checking. So if you have a Suslin measurable coloring of all infinite dimensional subspaces, there's infinite subspaces all whose further infinite subspaces are same color. So this is the analog of the Carlson-Simpson dual of the infinite, or Galvin-Prickly dual. Carlson-Simpson is a dual Galvin-Prickly, and so this is that level for the tree. So, okay, I think that this would be a good place for me to stop. I should ask for a question. Yes, okay, sure. Questions are, of course, welcome. More than welcome, yes. Yes?
What would be the next type of structure up?
Yes, okay, good questions. Okay, you see, people have looked at the dual structure. People have looked at the structural Ramsey theory and tried to simply dualize the proofs. And it worked for quite a while. The only problem is that it never worked when you had a forbidden structure. You simply get a model with no forbidden configurations. And typically application, you need them. So, for example, tree is giving you forbidden configuration, saying you must split this that way. I don't want any sequence of blobs. So the next, okay, so after the tree, of course, the next will be, okay, so let us see, be careful about that. What I would do next? I think that I will go to the finite theory and go to, well, try to prove my favored dual Ramsey theorem, which is the following. I think there's a problem or a conjecture of three of us. Because I think it's a good test. It's a good test, what I mean for forbidden configurations. And it's also, it's so simple that you can actually not forget, you're not going to forget if you leave this room. Okay, so problem, prove, or is it, or simply for a project, or prove, finite, dual Ramsey theorem. Meaning Graham-Rothschild, remember Graham-Rothschild was about the partitions. You're coloring the K partitions. And you're having the L partitions, all whose case partitions are more hermetic. Finite dual Ramsey theorem, meaning the Graham-Rothschild. For forbidden structure, equipartitions. So all pieces equal size. Typical good. In other words, prove that for a finite measure algebra there is a Ramsey degree. Finite measure algebras form a Ramsey class if they're homogeneous. That's typical application of such a result. This would be rather a useful result for many contexts if you have. Part-type construction, the typical thing that worked in the injective structure Ramsey theorem plus the dual version of it is far away from being able to attack this problem. So this is the good thing to start. Yes?
Is it interesting to know how fast the integer bounds that you...
Yes, that's a good question. Yes, we were quite surprised by the complexity. We were surprised by the complexity of this result because by the complexity of the moves in this result. In this result, we had to invent three different versions of the Hell-Jewett theorems for the trees. So three different versions. One version for the tree with a point inside, with the tree with a point on top of it, and simultaneous versions. So each of them gives you the usual, so at the moment is the Ackermann level. There's a double or triple induction. So on that level we are. So we definitely not primitive. Our proof don't give primitive recursive. So at the moment, and yes, it will be difficult. We had enough trouble with this to conjecture that you can actually prove it, but I will not be surprised if tomorrow somebody looks this from quite different angle. So at the moment we are at the Ackermann level, several induction of several parameters. And by the way, this is the good that you mentioned this because somehow this tells you why would typically when you think from the experience with Ramsey theorem. Typically, a Ramsey theorem is easy to prove infinite because of this fact. But here is opposite. The reason is because you have many more parameters to go induction on. While if you have an infinite, there is only one direction you're going, only one parameter. So meaning that if you don't really understand your situation, meaning the induction, here we are doing induction on several of these. And that was why we achieved the first finite form. Of course, infinite one implies this. Of course, without bounds, without real bounds. But the infinite one is stronger than this one, but is much more subtle. And there you actually need new ideas. Okay, I can let you go. I hope I left enough space for the next speaker. I think a few minutes, sorry about
So we have a 3-minute break.
5 minutes. 5 minutes?